Valve's Steam Machine reservation queue is launching today for $1,050 for a 512 gigabyte model and $1,350 for a 2 terabyte model. They also have controller bundles. We'll put the conclusion up front, no bullshit. In GPU-bound gaming performance tests and with SteamOS for the machine versus our standard Windows bench, we found the Steam Machine performed closest to the RX 6600, Intel B570, and RTX 3060, with one instance of an RX 7600 match. The most immediate cards ahead of the Steam Machine and from modern generations were the RX 7600 and RTX 5050. It's not particularly powerful, mostly because it literally isn't powerful. Valve is limiting the TDP pretty hard on these parts due to the PSU capacity and for thermal reasons. Power consumption has it in the range of 170 to 180 watts gaming and in the low 200s for full torch or load, but that drops within minutes of starting. Thermally, the Steam Machine did better than you might expect with its closed-off front plate, but we were able to improve CPU clock boosting by dropping temperatures several degrees with a mod that we 3D printed. CPU performance and Stellaris simulation time benchmarking had the Steam Machine at around the level of the R7 3700X or R5 3600. Decompression testing had it at the R5 2600's level, with Blender putting it near the 5600X. Those are the key details up front. We have a lot of commentary on SteamOS as well, but we also have a lot of testing to do today to prove our work, including the fan tester to test the built-in custom fan that Valve's made for the Steam Machine. So we're using this to evaluate the pressure and the flow of the Steam Machine. Part of the testing includes mounting the back of this to the front of the fan tester, bypassing the Steam Machine, plugging the fan into this that we've wired up with an adapter cable going to the Steam Machine fan, and then using all of that to measure how the built-in Valve fan performs against the actual heatsink. This also includes testing for pressure and flow against the different faceplates, so the default one, which is just a solid wall that Valve includes, and the GN downpour steam vents that we made, and actually we are launching these on the store today. We printed over 100 samples of the different front panels and fan mods, and then I tested some of them for thermal performance. So for that, in addition to just doing all the Steam Machines, GPU, CPU, SSD, Wi-Fi, all of the thermal numbers for the box as shipped, we ended up wiring up a bunch of thermocouples too. So we have some of these that are going to the internal chamber underneath, because it's a dual chamber box basically. And then we're also collecting ambient actively, and we collect the exhaust temperature as well through a thermocouple logger. We synchronize that data with the internal sensors of the CPU and the GPU, and that allows us to look at if Valve is achieving okay thermals considering the size of the box. But really the way that they're getting the thermals they are, which are pretty good overall even with the solid plate, is by driving down the power consumption of the whole device to be low TDP, which reduces the performance but does improve the thermals. Since it's a small, potentially living room PC, basically like a console type of situation, we also want to measure the power consumption. So we did a bunch of power testing on it for gaming and for full torture workloads. We also did Schlieren Imaging on it using the mirror back here, which we'll come back to that in a minute. And then the rest of the testing involved our hemianechoic chamber, where basically we set the mic up to a 1 meter distance away from the Steam Machine and measure it with the different plate options. But more importantly than our own is just testing Valve's, because Valve made a lot of claims about the acoustic performance of its Steam Machine back when we visited them in November of last year. And that's gonna be important, because if this is going in a living room or a bedroom setup where the tolerance for noise is lower, it needs to be quiet. And they're running off of one large 120 millimeter fan that is custom molded into a relatively wide fin spacing fin stack, which allows it to deal with the resistance to flow better, because since the fins are wider apart and because the fan is tuned to basically be a higher pressure fan rather than flow focused. Schlieren Imaging allows us to see the behavior of the air around the Steam Machine. So for example, we can see the air density gradient on our other camera there by using this parabolic mirror matched with the source of light. So the setup is camera to capture, pin source of light through an aluminum foil with a hole punched in it, razor blade to help cut the light in half, not because it's sharp, attached to a tripod. And then on the other side, we have this parabolic mirror, which produces the magic that is Schlieren Imaging, and it's gonna allow us to see how the air changes around the Steam machine, specifically because it's actually pulling a lot of the air through the bottom. We brought you this video with our Steam vent plates that we just launched on store.gamersnexus.net. These improve CPU and GPU thermals of the Steam machine and add a dust filter while supporting our in-depth testing and our local team of 9 directly. We fully modeled the Steam vents in-house, including months of R&D on design, structural rigidity, and slicer settings because we're 3D printing these ourselves. Our team here hand installs the 4 magnets with 3M VHB backing in each plate we print and preps the dust filters that we custom designed. Because Valve doesn't include a dust filter for the machine and it has gaping holes in the front. The Steam vents come in a variety of colors, including blackout, a purple-blue color shift, orange box-esque color shift, an obnoxiously vibrant tricolor, stone-colored grille, silver blades, and a few blues. Our design is directly inspired by the Fractal Torrent, the best-performing ATX case we ever tested, and our homage is named Downpour. 3D printing is what allows us to move fast and make so many color combinations because we don't have to hit high minimum order quantities. It also eliminates wasteful freight hops and price hikes, tariffs, and bullshit because we just print it in the office and have our existing team oversee production. Then we bring it to the local warehouse team for assembly. It's also easier for me to sign these since we make them here. So I'm going to be signing the first 500 that we print and then we'll distribute them randomly across orders over the next few weeks. We're also including a 7-year warranty, so if you have any problems with the plastics or dust filter at all over time, just email us and we'll swap it for you. The warranty even covers accidental damage, so if you drop it into a vat of acid, send us a photo of the charred remains and we'll send you a new Downpour Steam vent under warranty, as long as it was by accident. If you're wondering if our product is necessary, the answer is no. It's completely unnecessary, because Valve did a pretty fucking good job on the thermals and you don't need to buy ours. But we did an even better fucking job, and we have a ton of data to prove it. The end result is more color options, better quality control, and more of the money goes directly to my team locally to keep making videos. Grab one on store.gamersnexus.net. Back to it. Valve shared an early draft of today's blog post with the press, detailing the queuing system for purchasing and the pricing. It included lines like, quote, "The price at which we sell our hardware is a direct result of the cost of these components. We found we couldn't source some of our components at all at any price," end quote. That's not a surprise, but it sets the mood. We have a 3.5-hour long documentary covering the collapse of personal computing and the pricing, and that pricing is affecting Valve here as well. We'll link it below. Valve put some spin on its explanation of why it wouldn't subsidize the machine as well, saying, quote, "When companies sell their hardware under cost for competitive advantage or buy exclusive content for it, they're doing that to build a more closed system, one where you don't get to choose what software you want to use. We don't want that for PC hardware, and we don't think you should want it either. You shouldn't feel like you have to buy Valve hardware. You should be able to view it as just one option alongside all the devices for playing games," end quote. This is making the best of a bad situation, but we could also imagine Valve getting criticized for undercutting smaller manufacturers at $600 at a time when it's in a lawsuit over alleged monopolization would harm the credibility of its defense. So their choice of publishing it this way makes sense from a legal standpoint as well. With the actual prices of the Steam machine, we definitely don't think they're in any danger of looking like they're unfairly undercutting people. Most of the rest of the post explains the complicated queue system Valve set up to combat scalping. If you sign up before June 25th, you get a random chance to be put in a randomized reservation queue, not chronological, and the overflow gets put in the queue to get into the queue. The randomization is a good thing, as it means you don't need to be at your computer at minute 0 or minute -1 for the controller, as there's no advantage to pre-ordering at the first minute versus pre-ordering 8 hours or a day later. The bottom line is that you don't need to rush too much if you want this, and scalping will be harder than usual. If you care about the finer details, they're in Valve's blog post. Valve finishes by answering the question, if I don't get a Steam machine right away, is there anything else I can do? By basically saying, yeah, use your own computer. The new SteamOS 3.8 release is compatible with some non-Valve hardware as long as it's not NVIDIA. That's mostly because NVIDIA drivers on Linux are a nightmare, not because of Valve's own choices. The Steam machine uses a 6-core, 12-thread Zen 4 CPU with a max advertised boost clock of 4.8 GHz with a 30-watt TDP, which will be its largest limiter. The GPU uses RDNA 3 with 28 compute units, a 2.45 GHz max advertised sustained clock, a limited 110-watt TDP, and 8 GB of GDDR6 VRAM. I/O includes ports for 4 USB Type-A, 1 USB-C, a micro SD card slot, 1 HDMI and 1 DisplayPort, and a 1 gigabit Ethernet port. We were surprised and a little annoyed that Valve opted for a 1 gigabit port for Ethernet when 2.5 gigabit Ethernet is increasingly common, even on low-end motherboards now, And although most people aren't on an internet connection this fast, including us, Steam supports transferring games intra-network without a re-download to the outside web, and LAN speeds greater than 1 gigabit per second are becoming increasingly common. So it seems like a cost down to us. Valve ships with 16 gigabytes of DDR5 5600 RAM, a 300 watt power supply, and its 2 SKUs have either a 512 gigabyte or 2 terabyte NVMe SSD. RAM is the biggest problem. Not only is it limited to 16 gigabytes of DDR5 5600, but Valve broke news to us that it would be shipping Steam machines with either a single 16 gigabyte stick or 2 8 gigabyte sticks. The obvious problem with this is channeling. Memory in dual channel will objectively perform better than single channel, although Valve claims that gaming benchmarks didn't reflect much change.
The memory that's populated in the slots, like, at some point you might have 2 DIMMs, at some point you might have 1. It just changes based on the supply that we can secure. But at the end of the day, it should be comparable speeds and all that.
Okay. Yeah, just to be clear, basically, the system memory is 16 gigabytes. But again, to be able to build as many as we can, we have to essentially have some with 1 stick, 16, some with 2 sticks of 8. I mean, we validated the performance delta, and we don't really think it makes a big difference, or if any measurable difference at all. I mean,
for games work. If you're doing workstation stuff, the memory stuff, we understand that dual channel has a difference there, but the wall clock time difference for real games is not. At least we thought it was worth it. It's either that or all the machines that have 1 slots, we couldn't have shipped them. So I think it's worth the trade-off. But that's definitely that's impacting it for sure.
Yeah. But obviously the 2 slots are there if anybody wants to use them or whatever.
Yeah, it's a little bit of a weird trade-off because it's like having 1 stick is actually better for some cases because some people might want to upgrade to 32 and now they can just plop down another module. Right? So it's a little bit of a trade-off either way. But right now, because we can't really decide on just one, and we have to just take the supply that comes in.
We'll do some additional testing with single-stick options, hopefully this week, and publish that in a follow-up. Market conditions are bad, though, and Valve is a nobody in the world of system memory purchasing. In fact, memory module maker G.Skill, whom we interviewed for our Collapse documentary, is also a nobody, and their entire business is literally purchasing memory. The companies getting priority are NVIDIA, OpenAI, and other hyperscalers and data center-type companies. Valve does not get contracts with Samsung, SK Hynix, or Micron, who collectively control almost the entire DRAM market. We actually have a documentary about the DRAM cartel. We spoke with Valve about that for a separate video coming up, but here's the important part. Were you able to lock in kind of contracts for memory with the suppliers directly, or did you have to jump through a bunch of hoops? Or
look, there's no contracts, there's nothing. Yeah. Like those guys, they are, they give us a price every month or something, and they say, you can buy that many, and it's yes or no. And if we say no, then they never talk to us again, right?
So the RAM situation is out of Valve's control, or anyone's control, other than like 5 companies, basically. Here's a pricing breakdown of the Steam machine as compared to the DIY price of a similar system by paper spec, which is different from a system by performance spec. On paper, the Steam machine's semi-custom CPU and GPU are most comparable to AMD's R5 7540U and RX 7600M. These are laptop parts, so that's no good for DIY pricing. The most comparable new desktop hardware, other than OEM parts, so we're talking things you can actually buy retail, would be AMD's R5 7400F and RX 7600. The 7400F matches the Steam machine CPU architecture and core count and has a similar max boost clock, but it has a noticeably higher 65-watt TDP. The machine is heavily power limited. The RX 7600 matches the Steam machine's GPU architecture, VRAM, and clocks, but it has 32 compute units instead of 28 and a higher 165-watt TDP instead of 110 watts. We had to get creative with suitable replacements for Valve's proprietary CPU cooler, motherboard, and case. This isn't a spec we necessarily recommend, the one we chose, just close in parts. Compared to our DIY equivalent systems, the 512GB Steam machine's premium over DIY is $71, or roughly 7.3%. It's $211, or 18.5%, over DIY for the 2TB configuration, which also includes the 2 extra plates. In reality, though, Valve doesn't perform anything like this system. The Steam machine is far lower in performance than this equivalent build by paper spec. Valve's premium over DIY for a new build doesn't look like much, but the comparison's also not simple, since the parts are all semi-custom and power limited. For additional reference, HP sells its Omen 16L with an R5 8400F, RX 7600, 16 gigabytes of DDR5, and 512GB NVMe SSD for $1,350 at the time of writing, which makes Valve's 512GB Steam machine $300 cheaper than HP's comparable but power unbound offering. Here's a look at steady-state GPU thermals using delta T over ambient values for A/B comparisons. Out-of-the-box test with a solid panel, feet installed, and the auto RPM, which resulted in 1252, put the Steam machine at 23.5 dBA at 1 meter. GPU edge temperature held 42 degrees Celsius over ambient, junction was 57, and VRAM was 46. With ambient, those are about 62, 77, and 66 degrees. The GPU and memory are both within spec. Running auto RPM, but without a front panel, put the machine at 37 and 51, so a 5 to 6 degree improvement, while also reducing the fan by almost 100 RPM, which told us that there was room to improve on Valve's design. Normalizing RPM to 1252, our downpour mod improves thermals by 6 to 7 degrees, at 36 degrees edge, 50 junction, and 40 VRAM. Our noise level's higher at the same RPM at 27 dBA versus 23.5 dBA, so Valve prioritized the noise. Most people are able to perceive noise changes at 3 dBA increments, so the downpour is louder but much cooler. We achieved slightly better thermals and better dBA SPL noise against the stock plate by setting the fan curve to max out at 1050 RPM instead. Noise reduced to 23 dBA and temperature reduced about 1 degree on the GPU. Running auto with downpour into filter, we improved by about 1 degree on the stock panel while now filtering dust. This is with a 0.5mm hole spacing on the filter, but our finals will be somewhere between 0.8 and 2.0. We're not sure yet, but that'll improve the thermals. Max fan RPM at 2000 pushes the solid plate machine to 35.4 dBA, a whooshing noise, and a 42 degree junction temperature. Downpour hit 38 degrees, 38.7 dBA, but without the wind whooshing noise. We wouldn't recommend, though, 2000 RPM regardless. Removing the feet only had a 1 degree impact to GPU thermals. This will be pretty interesting later. And as much as we'd like to sell our own improvements that we've made, we really have to give credit to Valve for doing far better than we expected with the solid front panel. You don't need our plate because this isn't thermal throttling stock. We'd love to sell it to you, but you can definitely just use the Steam machine out of the box without thermal issues, as long as it isn't on carpet. That's really key here. If you jam the bottom, you're gonna have a bad time. CPU is up next. The fully default Steam machine ran the CPU at 50 degrees over ambient for TCTL, or about 70 degrees with ambient, which is fine. Running our front panel RPM normalized puts it at 43, 43, and 49, a significant CPU temperature improvement at the cost of more noise. 1050 RPM drops noise levels below Valve stock and improves thermals about 1 to 2 degrees using downpour. Adding the high density 0.5mm filter put it back at parity with Valve's default plate, except now the Steam machine is filtered for dust. There's headroom for Valve to have boosted the power budget more for performance here as well, but it's likely targeting the worst case scenario and the power limit of the power supply. But again, we'd still like OC options. What's not shown in the previous charts is the clock speeds, which are impacted by temperature. This chart shows the average CPU clocks across the highest cores and all cores. Our downpour panel at 1252 RPM improved clocks to 4047 MHz high and 3505 MHz all average, with the like-for-like comparison to the stock panel at 1252 RPM at 4001 MHz for high and 3467 MHz for all. At 1050 RPM, we're at roughly noise parity with similar thermals. The downpour panel improved to 4012 MHz, not much, not really noticeable, technically present. This is after the clock drop from the TDP limiter, which we'll come back to. Here's where Valve's design gets really interesting and actually pretty clever. Stock plate NVMe SSD temperature measured 9.9 degrees over ambient. Removing the front panel, which dropped the RPM to 1164 due to reduced CPU thermals, resulted in a warmer SSD temperature despite improved CPU and GPU thermals. That's mostly because the front panel was increasing the resistance at the front of the chassis, which forces air to move through anywhere else it can find, and that's the bottom of the machine. That cooled the SSD. Ultimately, an SSD's flash memory actually prefers warmer environments, not colder, and the controller is cool enough to not matter. So opening up the front panel is better for the device overall when given the trade-off option. Going to our plate at 1252 RPM, we saw an increase in SSD thermals of about 3 degrees Celsius to 12.9 from 9.9 stock. 12.9 degrees would be about 31 degrees or so with the ambient included. So way below operating spec limits of the SSD while still improving CPU and GPU thermals about 5 degrees, but we did objectively make the SSD temperatures a few degrees worse with this plate. Very cool, though, to see the pressure science in action. Unrestricting the front intake improves GPU, CPU, system memory, VRM, MOSFET, and capacitor thermals, increases SSD thermals, and using the solid stock Valve panel and removing the feet actually hurt the SSD temperature unlike CPU and GPU temperatures where there was basically no impact. This is also due to the temperature coming through the front instead of the bottom. So this would be your stand-in for a carpeted test. Really need to make sure it's not on a thick residential type of carpet. Noise tests in the hemianechoic chamber are next. This first chart shows dBA SPL levels over a 30-minute burn-in. For the first 3 minutes, our total system noise level at 1 meter in the hemianechoic chamber was roughly the noise floor on the day we ran the test. In other words, at idle, the Steam machine is effectively inaudible. If you have literally anything else in your house running and you're sitting on the couch, you probably won't be able to hear this device. Once it hit the workload, it climbed over about 5 minutes to steady state thermals and RPM. The fan ran about 1252, held 23 to 24 dBA noise level for the remainder of the test. The gaming test with Black Myth WuKong had it steady at about 20 to 21 dBA, so notably quieter on an already quiet system with the solid front panel. For reference, several of the higher performance full tower pre-builds that we've reviewed over the years operate in the range of 30 to 35 dBA in this test, but while cooling much more power. This is the frequency spectrum plot for the stock machine with auto settings. Under a full torture load and 1228 RPM, the machine showed a low frequency spike at 140 Hz, a spike shifted right at 210 Hz, a larger spike at 533 Hz, and another around 1000 Hz. The gaming load spikes at 123, 199, 521, and 908 Hz with its 1125 RPM. The fall off is similar between them. The spikes don't line up perfectly with blade pass frequency against the 5 struts, but some of the harmonics are close, like the 210 Hz and 199 Hz spikes. Our downpour plate is nearly noise normalized for dBA SPL at 1050 RPM, so we'll plot that one here. The downpour plate, when dBA normalized, exhibited similar frequency characteristics above 1800 Hz. Our plate has its peak shifted left towards 117 Hz instead of 140 Hz for the direct comparison. We also see a lower noise level in the range of 200 Hz to 400 Hz, which is the low whooshing sound that we described earlier as generated by the stock solid Steam machine faceplate. The downpour plate is quieter in this range when normalized for levels. We saw a similar spike at 500 to 600 Hz as the stock plate, but ours was louder in the range of 700 Hz. All right, moving on from the plates. During our acoustic testing, we logged the power from the wall as well. The full system was drawing 13 watts at idle in the lead up to the looping Black Myth WuKong benchmark, and once the test began in earnest, it reliably ramped from 173 watts to 176 watts during each loop, with obvious dips down to approximately 50 watts between the loops during loading. With this workload, there wasn't any discernible difference in power draw from start to finish across the 30-minute load period. Valve has a 300-watt power supply, so pulling 176 watts is definitely well within its capacity. Also, the 13-watt idle here is at desktop for, well, gaming mode for SteamOS. If you have it off but in standby, we measured that at less than 1 watt. The full torture test, utilizing Blender as a CPU load and firm arc for the GPU, ended up with a different result here. Full system power draw, once the load was fully launched, shot as high as 209 watts, then dropped sharply down to 192 watts after a couple minutes. This seems to mostly be due to CPU limits, as we logged CPU clocks and temperatures dropping at the same time, while GPU values remained relatively constant. We weren't thermal throttling, but 209 watts, despite being still well within the capacity of the power supply, is a good reminder as to why Valve maybe hasn't unlocked the power target controls with the PSU choice it made, because at most you might get an extra 40 to 50 watts before Valve would start feeling uncomfortable, probably pushing you too close to the tactical capacity limits of the power supply. We get back 12 CPU megahertz values from proc CPU info, meaning the numbers correspond to logical processors rather than physical cores on the machine's 6-core 12-thread CPU, but we can still use them to illustrate a point. 4 of the clock speeds boosted high and then dropped in sync with power. The other 8 remained basically flat across the whole test. We've picked one of each plotted here. It took almost exactly 4 minutes for the initial throttling, followed by a roughly 30-second period of decreasing clocks until abruptly dropping down to a steady state. We don't think this is a big problem since games don't typically keep the CPU fully loaded for minutes at a time, but it is interesting to see the kind of limited boosting behavior and mixed clock speeds that we associated with Intel processors of the past. This is a clear throttle, likely intended to prevent thermal issues. Really, the biggest downside would be if you were doing especially things that aren't gaming, like, say, rendering with Blender, as we showed earlier, because in those types of workloads, you will load the CPU sustained for long periods of time, whereas with gaming, Typically, the CPU fluctuates up and down. Game benchmarking is next. We usually benchmark games on Windows using PresentMon via command line, a well-established open source tool. We've had great conversations with Intel's Tom Peterson about how PresentMon and the graphics pipeline work, but a lot of that is specific to Windows, including the PresentMon software. On Linux, including Bazzite and SteamOS, we use Mango HUD for login, another third-party open source tool that Valve uses for its own SteamOS performance overlay. The Frametime numbers we get from Mango HUD work for a general comparison to the PresentMon numbers in Windows, but the caveat is that they are different tools, monitoring different graphics pipelines on fundamentally different operating systems. It's not perfect, and these are not a strict A/B comparison, but it's what we have to work with. We're still learning about Wayland and the way things like screen tearing are handled on Linux, so stay tuned for that in future videos. Resident Evil 4 is up now. This is another game where we have a massive amount of data due to its 3 years on the test bench. The Steam machine ran at 94 FPS average, putting it right around the same level as the 5700 Evoke from 2019. Lows are also functionally identical between them. The 2070 Super leads the Steam machine by a few FPS, with the 2070 Non-Super below it, and at 88 FPS average, around the same level as the 92 FPS from the 6600. The Steam machine ends up leading the 2070 and 3060 by about 6%, and the 2060 by 33%. As for what's ahead of it, the more modern RX 7600 ran at 112 FPS average for a lead of 20% over the machine. The A750 and RTX 5050 are also in this range. The Steam machine's performance, in an absolute sense, is overall okay, in that it's playable. However, it's weakly positioned in a relative sense. In Black Myth WuKong, we measured the Steam machine's holistic performance with SteamOS and the reporting differences at 43.9 FPS average, roughly tying the B580 and just ahead of the B570 from Intel. The RX 7600 ran at 47 FPS average, so technically an advantage, but they're comparable enough. The 5050 widens that gap despite being an awful video card, and the 6600 shows at least that the Steam machine is outperforming the ancient GPU with modern CPU combination. Comparing against older hardware, the RTX 3060 12GB is almost perfectly matched to the Steam machine, keeping in mind the CPU mismatch, but we're GPU bound here. Lows are also about the same. The RTX 2070 is nearly within error and variance. The Steam machine ends up being a blend of the RX 7600, RTX 3060, RTX 2070, and B580 in this chart. It meaningfully outperforms the 6600 and the 5700. In Starfield at 1080p Ultra, which is directly comparable to our GPU suite, the Steam machine ran at 41 FPS average and sat between the Intel A770 43 FPS average result and the A750 38.5 FPS average, also leading the 38 FPS average of the 6600 by 8%. The RTX 5050 without a CPU limit improves upon the Steam machine's performance by 19.8% for average frame rate, with the 5050 also improving upon the lows, which it has at 41 and 34 to the machine's 25 and 18, predictably. By scaling, it's also better. The Steam machine has disproportionately poor 1% and 0.1% lows in this test as compared to the average when scaled against other devices. This is atypical of games running on Proton, where we typically see disproportionate advantages against Windows. This happens sometimes, it just depends on the game. The RX 7600 remains our anchor point and leads with a 49.8 FPS average, or 20%. In Oblivion Remastered at 1080p Ultra, the Steam machine ran at 27 FPS average without any form of upscaling. Since we mostly care about the relative scaling and not absolute frame rate, that puts it as comparable to the 7600 and its 26.5 FPS average result. The Steam machine ended up with a technical improvement of 1.9% over the 7600. The frametime pacing is about the same between them, and the Steam machine leads the 2021 RX 6600 and its 19 FPS average by about 40%. In Kingdom Come Deliverance 2, the Steam machine ran at 50 FPS average, not bad in an absolute sense, and approached the B570 in average performance while running the same lows. That's a good thing for low pacing. The machine is still beaten by the CPU unbound RX 7600 at 59 FPS average, or a 19% advantage. In Dragon's Dogma 2, the Steam machine held a 52 FPS average with our 1080p max settings. Again, that's not bad in the absolute sense that you can play this game on the machine with these settings, especially if tuning the settings or using upscaling. In the relative sense, which is what we care about here, that makes it basically a B580 or A770 for performance, both of which struggled with this game. The RX 7600 leads the Steam machine with a 60 FPS average, or by 15%. The RTX 5050 is in the same spot. The Steam machine outperforms the older RX 6600 by a few FPS average, although more notably with the lows. Final Fantasy XIV Dawntrail's benchmark positions the Steam machine lower than we typically expect, but it was reproducible. The Steam machine ran at 86 FPS average with okay lows, but worse relative lows than devices like the RX 6600, which has the same average FPS. The machine ends up behind the 2070 and 5050, and far behind the 107 FPS average result of the RX 7600. We test the Outer Worlds 2 at 1080p very high, so this should be tuned down for real Steam machine use cases, but this is what we have months of data on, and so it makes sense for the best relative comparison. comparison. The Steam machine ran at 26 FPS average. More importantly, that has tied with the RTX 5050 and Intel B570 ARC GPUs. The RX 7600 leads the Steam machine by about 15% here, with the machine leading cards like the RTX 3060 and RX 5700 from an era past. Cyberpunk 2077 Phantom Liberty at 1080p Ultra is next. The Steam machine ran at 59 FPS average, about tied with the Intel Arc A750 and RTX 2070. The 3060 is just behind the Steam machine, and the RX 7600 ran at 68 FPS average, an uplift of 16.6%. We also tried running the F1 series of games, including F124, but were unable to get it to run due to the anti-cheat software being incompatible with SteamOS. And we also ran Total War Warhammer 3, but it had issues with the in-game framerate report mismatching Mango HUD, resulting in unreliable data. Ray tracing benchmarks are up now. We only have a couple. You'd really need upscaling for this to be workable, but everything scales relative to each other, so we'll stick to our approach for A/B comparisons. The Steam machine ran at 21 FPS average in Cyberpunk with RT medium settings. Again, that improved with upscaling and settings tuning, but the relative rank would not meaningfully change and may even get worse versus other devices. The RX 7600 ran 8% ahead of the Steam machine, but with worse 0.1% lows. The 6600 is just behind the machine in average, but also worse for lows. The RTX 3050, 3060, and 2070 all outperform the Steam machine meaningfully. Valve posted a last-minute ray tracing performance patch that we also tested. The Steam machine patch pushed it to 22.8 FPS average from 20.7, an improvement of 10%. It's a lot for a software update. We also ran ray tracing with Black Myth WuKong at 1080p high and using quality FSR settings. The end result was 14 FPS, so it's just not playable. Maybe on low settings and performance FSR, but RT in this game is really heavy, period, but especially for the Steam machine. Valve's last-minute patch boosted it to 16.7 FPS from 13.8. Although the absolute value is obviously low, this is a huge percentage increase of 21%. That matches Valve's expectations. SteamOS has historically improved upon frame-to-frame interval over Windows for handhelds, so we'll look at frame times individually as well. We'll start with one of the best performers, which is Kingdom Come Deliverance 2 at 1080p Ultra. 20 milliseconds per frame translates to a sub-60 but playable frame rate, and the 1% and 0.1% lows stuck close to the average as well, indicating few spikes. In contrast, this Starfield pass at 1080p Ultra wasn't much worse on most frames, but had some huge spikes, up to 40 milliseconds or more. The biggest spike logged in this run was just above 60 milliseconds. These are noticeable against the 22 to 25 millisecond standard. It's unfortunate that we can't yet log frame data with the same detail as we would on Windows, since this would be the perfect opportunity to check the animation error or simulation time error metric. CPU-specific benchmarks are next, where we take our standard CPU suite and run the Steam machine against it. These are intended to be CPU bound, but we can't isolate the GPU obviously totally from this, so there are instances where it still hits other limits. Keep in mind that CPU benchmarking also heavily depends on memory. All of our desktop CPUs are spec matched, but we're testing the Steam machine out of the box. That means some of the performance differences will be from memory, since we aren't isolating the components like we do for a desktop part, and there are no speed and timing controls. We'll start with 7-zip file compression testing measured in millions of instructions per second. In this test, the Steam machine completed 55,000 MIPS on average, putting it just below the R5 3600, which leads by 7%, and just ahead of the R7 2700 with a 1.7% advantage for the Steam machine CPU. The R5 2600 completed 46,000 MIPS, meaning the Steam machine is ahead by 19%. Valve's Steam machine may be a Zen 4 solution, but with its hard power limits in at least this test, it performs closer to Zen 2 and Zen Plus CPUs. In file decompression, the Steam machine falls below the R7 2700 and R5 3600 meaningfully, outperforming only the R5 2600 on our charts. The Steam machine ran about 7% ahead of the 2600. The 3600 outperformed the Steam machine by 12.5%, with the 5600X at 31%. The 7600 completed 103,000 MIPS, which looks impressive against the 67,000 of the Steam machine, and leads by 53%. Blender rendering with cycles on the CPU is next. In this one, we tested the Steam machine both with the like-for-like version of Blender with all of our other CPU tests, and with the newer 5.1.2 version. The comparable version is slower, but better for A/B, while the newer version may have optimizations for Linux. Like for like, the Steam machine required 24.4 minutes to complete a render of a single frame of our intro animation, which is basically tied with the R5 5600X3D and R5 5600X. We'll start with CPU game testing in Stellaris, where we can confidently test that we are CPU bound, not pushing against any kind of GPU performance limits. This helps us isolate the performance. The Steam machine with the same DX11 version of the game required 67.4 seconds seconds to complete simulation, which puts it between the R5 3600 and R7 3700X. The 5600X completed the same simulation in 24% less time. Using the Linux version of the game, the Steam machine improved to 63.9 seconds, a reduction in time required of 5%. It's likely that the other parts here also improve with the Linux version of the game. CPU testing for Kingdom Come Deliverance 2 is up now, tested at 1080p medium. The Steam machine ends up at the bottom of the chart. We haven't tested anything lower performance than the R5 2600 in a couple of years, and the 2600's 111 FPS average result puts it 31% ahead of the machine. Even though this is significantly higher in frame rate than the GPU-targeted testing we ran in the same game, it's possible that we're hitting the GPU limit now, but higher. Let's move on to another game. In the Outer Worlds 2, with our CPU-focused test at 1080p low, the Steam machine ran at 64 FPS average and roughly tied the R5 3600. The lows are nearly the same. The 3700X improves slightly, with the 5600X's at 73 FPS average, 13% ahead of the Steam machine's at 64. Overall, the absolute performance isn't bad for the machine, but paying this much money for effectively a 2019 R5 3600 computer in 2026 doesn't feel great. In Starfield at 1080p low for the CPU, the Steam machine landed at 65 FPS average with poor lows, disproportionately worse than those found on the R5 2600, minding the differences in collection and OS. We may be binding more on the GPU in this test, as our GPU-focused results had it in the 40s. On to SteamOS and BIOS. Even if you haven't used the Steam Deck, you may be familiar with the SteamOS interface since Big Picture Mode was updated to match. Valve told us from the beginning that its plan was to make the 2022 reboot of SteamOS available to install on non-Valve devices, like the 2013 original, and on desktops, but that plan has been moving slowly, with some exceptions like the Legion Go S and third-party hacks. Valve reiterated to us that it's opening up installs on third-party hardware. It also sounds like NVIDIA driver support is predictably tricky because Linux with NVIDIA, but AMD and Intel should be fine. Escape during the boot process enters BIOS, which is navigable with a Steam controller if you get one before 2027. Performance settings are entirely adjusted from inside the OS and are very limited. There aren't any controls for memory speed or timings within BIOS, which may make upgrading less precise. There aren't any overclocking options or TDP or PPT bypasses, which sadly limits the headroom of mods, useful overclocks, and competitive overclocks. BIOS consists of settings for S4 Wake on USB, S4 S5 Wake on LAN, and WLAN, Fast Boot, which is on by default, BIOS Splash logo support for presumably third-party Steam machines from OEMs and SIs, and USB hotkey support. LED options include a toggle, power, and strip LED brightness, with the strip being used for game and firmware downloading progress as a progress bar, strip effects, and strip colors. Valve's been short-sighted on its non-handheld deployment of SteamOS in several instances. On first boot, the machine immediately shows diagrams for connecting a keyboard and mouse, as well as a Steam puck and controller. After that, we couldn't get any further than language and time zone without an internet connection, and there might be a workaround equivalent to the OBE bypass for Windows, but considering the whole thing is built around logging into a Steam account, that wouldn't really ultimately accomplish that much. Before going all in on SteamOS, it's worth considering how you feel about a Linux distribution that's built ground up with an always online philosophy, even if you can use it offline, especially with Steam having an offline mode. If you wanted to install this on a standalone desktop that's not the Steam machine, you might want to consider something like Bazite instead, just because it's built with the however the fuck you want to use it sort of use case in mind. Logging in was the first reminder that the SteamOS UI was not built to prioritize mouse and keyboard. Every time we clicked a text box, the on-screen keyboard would pop up even without a controller connected, and every menu shows controller glyphs. Some mouse cursor icons were low-res and stretched at 4K, and dragging items around in the download queue made them teleport around. The quick access menu that contains multiple vital settings doesn't have an on-screen prompt, and the keyboard shortcut is the less than obvious Control+2, or on an Xbox controller, Xbox and A. SteamOS is still controller first, desktop mode works fine, other than some occasional flickery artifacts, the keyboard and mouse work, and it feels familiar to any desktop OS, including file navigation, typing notes, and generally navigating the OS. Since this could be used as a desktop, we'd like Valve to tweak the gaming mode UI to dynamically adapt to mouse and keyboard and not simply just support them. We'd also like to see multi-display support, which currently only works in desktop mode. The biggest issue we ran into was that the resolution for all games is capped to 1920 by 1080 out of the box. There's a maximum resolution for each game in its Steam configuration settings, which starts at the known and common resolution of default, meaning that it defers to the top-level Steam setting for maximum game resolution, which is also default, meaning, in this instance, 1920 by 1080. Although useful for capping the resolution on borderless windowed-only games like Starfield, the implementation just isn't clean or good. Valve told us that, quote, 1080p is the system default game resolution on Steam Machine to ensure a good gameplay experience out of the box, and is the resolution we use for Steam Machine verified testing, end quote. This led to a confusing situation where we had a system running at 4K connected to a 4K display, which would never show any resolutions above 1920 by 1080 with games in full screen mode. You can work around this, it's just confusing as an end user used to basically any other operating system. Responding to our feedback, Valve said it is, quote, currently working on UI updates to help customers understand what resolution their games will launch at and how they can easily change this setting, end quote. The fact that the cap is tied to the Steam Machine verified program makes us worried that they won't change it, but it should at least be less confusing. Speaking of the verified program, our feeling that Valve has been short-sighted is growing. We had wondered what the long-term plan was when Valve launched a verification program around a single deck hardware configuration that labels over 100,000 games with, quote, Steam Deck compatibility, end quote, and the answer is apparently that it's just adding another verification program, which seems unsustainable given the inevitable Deck 2, although since Valve can't count to 3, maybe it's not that unsustainable, but then they run into the problem of Legion Go S and other official SteamOS partners. There are other signs of ill-preparedness. All the directories and usernames on the Steam Machine contain the word Deck, which it isn't, and every time we ping the sensors, we get an error because one of the Steam Deck sensors isn't present because it isn't a Steam Deck. Valve was supposedly always planning to distribute SteamOS on non-Deck devices, so they should have built this without those dependencies and artifacts. This is bleeding into game functionality as well. There's now a per-game disable Steam Deck auto-detection toggle, which may be necessary for games that see the Steam Machine running SteamOS and, for example, automatically disable mouse inputs like Kingdom Come Deliverance 2. Even with the toggle, there can be dev-side issues like Dragon's Dogma 2 and Resident Evil 4 detecting Linux and then disabling ray tracing, or Baldur's Gate 3, temporarily assuming that literally all Linux users ever are on SteamOS. Also, games like Total War Warhammer 3 will default to downloading native Linux builds whenever possible, even if those builds are worse and sometimes out of date than just running the Windows builds through Proton. To us, this is just messy, especially with APKs shipping on Steam for the ARM-based Steam frame. Valve laid the groundwork for a single device and type, so these artifacts are showing up in things that aren't those device and type. As for running software, we didn't run into any major differences versus the Steam Deck, other than higher performance, of course. We ran into some issues with DX11 games stuttering and presenting a lower frame rate than they should have, but that's not a surprise. Proton is a huge leap for Linux gaming, and sometimes gaming period, but sometimes it still takes legwork to find the right combination of Proton version and other settings, like disabling Steam Deck auto detection or FPS caps. As usual, some games, like F1, are completely incompatible due to their anti-cheat software. Valve has made some console E updates. The Steam Machine can be turned on by activating a paired Steam controller, which is actually pretty cool, and although that does mean that the machine is technically always on unless it's unplugged as confirmed by the manual, it draws 1 watt or less in standby. By default, the machine is set to finish downloads in a low power state when shutting down. Despite the disorganization in many places, we like SteamOS overall, and we especially like seeing Proton making Linux a viable option for gaming, with Proton having significantly improved Frametime pacing over the years. When it works, it's often better than Windows for gaming. It's just kind of messy the way that the greater OS wrapper is deployed. With Schlieren Imaging set up to image the air density gradient at exhaust, we can see a relatively conical, wide flow out the back of the machine that pushes air far away from the box rapidly. The key thing we're looking for is whether the warmed air can get away fast enough that it doesn't recirculate. Here we see that it does. The air goes basically straight back and in a cone at fairly high speed, so you'll want to give this some room from the wall to ensure it doesn't just ricochet off the wall and find its way back in. With the valve plate on the front, you can see some of the air is going up and over the front panel. Some goes up and then down into the small slit at the top, and a lot of it is actually flowing towards the bottom inlet between the feet. Taking the front panel off altogether, you can see the impact to flow. Air predictably finds its way straight into the machine because there's not a solid wall there anymore, although mostly biased up and towards the top half due to positioning of the internal components. Switching to our steam vent downpour plate, it doesn't change much, which is by design. This is basically an open front panel with some smaller obstructions. Finally, as I moved the machine to rotate it with the front plate on, you can see how the air follows the opportunity to enter the bottom, where the reduced resistance creates a lower resistance inlet path. Finally, some quick fan machine tests. Referencing our ModMats wiring diagram for PWM 4-pin, we built an adapter cable to convert the Steam Machine fan into a standard-sized 4-pin header and test it on the fan machine. We have more of these coming up in a separate video that includes mounting the steam machine itself to the fan machine. This video is running long enough already, so we'll keep it short. In this quick chart of max P and Q, the steam machine fan exhibited unbelievably powerful pressure at 4.79 millimeters H2O at 100% speed. We've never seen it automatically reach 100% speed in use, but this makes it clear that Valve designed this as a high-pressure fan first and foremost. Compared to the Noctua NFA12 G2's 3.23mm H2O, the machine's fan has higher pressure, but also higher noise, because the NFA12 G2 ran at 37.4 dBA at half a meter, and the Steam Machine's fan outside the box ran at 49.5 dBA at half a meter. It's much louder at full speed, and this was captured at a similar RPM to the NFA12 G2. Noctua's fan is just that much quieter. Noctua's CFM flow performance is also higher at 65.1 to Valve's 48.1. These are typically inversely correlated, and Valve favored pressure to flow. Just for fun, we ran a voltage limiter to the Valve fan to force it to 900 RPM outside of the machine, which noise normalized it to Noctua's full-speed noise levels. The pressure is far lower than Noctua's at 1.11 millimeters H2O, as is flow. We didn't capture noise for the nominal operating speed of 1252 RPM when outside of the machine, but performance was 2.12 millimeters H2O and 26.7 CFM. What may change is when you put both against the Steam Machine fin stack, as that creates real-world resistance to performance. We'll test that in a separate video. All right, so a lot of charts, a lot of stuff we looked at today. The two main ways to look at the Steam Machine are either as a console, I guess, alternative or competitor or companion, cube. They really should have capitalized on that. Or as a DIY PC, and we're obviously more familiar with the latter. So we're going to take the PC comparison approach, the DIY approach. We'll leave some of the head-to-head with something like a PS5 to others. From that perspective of PC gaming, we've shown that you can put together a box that would perform better than the Steam Machine in terms of FPS for the same amount of money or less. The machine isn't massively overpriced for what it is versus the awful market conditions, but it's not swooping in to save the struggling gamers either. Recapping performance in gaming, the GPU-bound performance lands the Steam Machine as about the same as an RTX 3060 12GB, A750, RX 6600, RX 5700, or frequently the Intel Arc B570 in our testing. Typically, we saw the most immediately ahead parts by relatively modern generation as the B580, RX 7600, or RTX 5050. The most immediately behind in our tests were the RTX 2070, RX 6600, RTX 3060, and RX 5700, among some others. Unfortunately, RTX 3060 12GB used GPU prices are unbelievably stupidly high for how old they are, and we can thank Lord Jensen for his impact on the GPU market.
I love getting rich.
Ladies, this guy has no money.
In CPU performance testing, we found that the Steam Machine performed similarly to the R7 3700X in Stellaris simulation time testing. In compression, it was similar to the R5 3600, and in decompression, similar to the 2600, Blender Cycles had the Steam Machine between the 3700X and 5600X 3D, just ahead of the 5600X. Valve had excellent acoustic profiling for the Steam Machine, clearly using its solid faceplate as a means to block noise escaping out of the front. This helped with noise levels, which are effectively silent when idle and not loud under load, but also frequency spectrum. This is at the cost of thermals though, where we were able to improve thermal performance by 6 to 7 degrees with our panel we're selling on store.gamersnexus.net, which also supports us and our in-depth testing directly. But this revealed that the SSD temperature increased with better flow to the CPU and GPU. Valve made bottom intake the easier path for air to flow in, hitting the SSD first, but worsening core component temperature. The SSD doesn't need that much cooling, and NAND actually lives longer if it's warmer anyway. We spent a lot of time talking about SteamOS in this review already. The quick version is that we like it, and we like the direction it's going, but that Valve has created a nightmarish, disorganized mess for itself by not building for its known future of a desktop and instead framing everything around handhelds, which from the start it knew weren't going to be the only thing with SteamOS. As SteamOS becomes more common and more devices are supported, both Valve and developers have a lot of work to do to ensure that correct, compatible versions of an incomprehensibly vast catalog of games are delivered. If Valve wants to capture a console audience, it can't rely too heavily on submenus for disable Steam Deck auto detection and manually selecting a Proton version to forcibly download the Windows build instead of the outdated Linux build when your buddy just wants to come over and play Borderlands 2. Our only really specific criticism of SteamOS on the Steam Machine is that system-level resolution cap for games should default to the native screen resolution, not 1080p, or at the very least, it should show what the default cap is. It's a weird choice given the marketing.
Enabling 4K gaming at 60 frames per second with FSR.
FSR obviously helps, but you still need to increase the resolution cap to get 4K output. It sounds like Valve is working on it, and things may be changed by the time machines ship to customers. So where they exist, the real advantages of a Steam machine over a DIY PC are that it's pre-built, if that's your thing. It's really tiny, if that's your thing, which is done by customizing the components in it. It has ongoing and active SteamOS support. It's pretty easy to get into and maintain and take apart. They are going to enable a bunch of separate parts purchasable from iFixit, for example, to do internal maintenance. I think they may have other partners as well. iFixit's the one I know of. So these are all good things. Really the main reason to buy this, though, honestly, is just because it's fun. Because if you're into computers and tinkering with things, then it's fun to have something different. This is a tiny box. It's uniquely designed. It's got a different operating system on it. I don't know if it's $1,350 fun, but it's fun to mess with it. I think that's probably a lot of the audience. It's not a good value in terms of performance you get for the money. DIY is going to be better than that. It's going to be probably larger, almost absolutely larger than this. You can still do ITX, of course. Buying used opens up a lot of options, but even those prices are stupid right now. I mean, memory, 16 gigabytes of RAM, similar to this. Bottom of the barrel is like $240 fucking dollars. DIY, like that destroys the price of anything. So awful market right now to launch anything into, but also to build stuff, unfortunately. Anyway, you can feasibly put SteamOS on some DIY solution if that's the only part you wanted. The box isn't bad, but it also isn't a savior. The best thing coming out of the Steam machine, like with the Steam Deck, is the software development, where Valve has done an enormous amount of work that is commendable on Proton, which has enabled a lot of games to just work in Linux and all kinds of different builds. Proton has also improved Frametime consistency, frame pacing over the years for, say, the Steam Deck first, and now we see that in the Steam machine as well, so that's great. And they've done work on GPU drivers, and they build the operating system itself. So it's a good time to be a Linux user. As for repairability, we'll talk about that more in our teardown tomorrow. It is overall looking good, though. We've seen the interest in using Steam machines as a living room client for streaming from a gaming PC that you've built separately. Saw that online. That is not unique to the Steam machine. You could do that with a lot of things. Anything that runs the Steam client or the Steam Link app can use remote play. So if that's all you wanted, you could do something else. Valve markets this as a host system, potentially for the deck or the frame. Here's a screenshot of the VA info output for the machine. Based on this, it looks like it's capable of H.264, 265, and AV1 encode decode. We understand the RAM shortages better than most, I think, and I've filmed multiple documentaries on them. That said, Valve is shipping some machines with one stick of 16 gigabytes instead of 2 of 8, and that is going to be an objectively worse configuration from a performance standpoint. I don't know yet how much or if that'll show up in games. It may be different in, how this is deployed and used in the real world. We'll test that in a follow-up video. We got to get some RAM in for the AB, but we're working on that. One quick note on the I.O. that didn't fit elsewhere. We already knew this, but keep in mind that the machine has no discrete audio outputs, not even optical. Audio has to be handled through HDMI, DisplayPort, or USB, which may be annoying for desktop users. Also, the rear two USB Type-A ports are USB 2.0, while the front two and Type-C are 3.2. So that's kind of it. From a value perspective, this is worse than you could DIY right now. It's not that far off. Like their overage against DIY parts is not as completely insane as some of the system integrators we've looked at over the years. Obviously, the big difference with this is it's not really upgradable. You can do the RAM, SODIMMs, you can do the SSD. It's not a whole lot else in there you could swap. I guess the fan or something, but it's not like you're going to do a CPU or GPU swap. They're not socketable. So, from a DIY standpoint, it should be a little bit cheaper, maybe roughly the same depending on the parts you're buying, but there's a big difference in how you interact with those devices physically. And some people are going to want, more of the it's built for you experience. And then I think a lot of our audience will want the DIY approach. I think the Steam machine is fun. I think it's interesting. Patrick and I have liked messing around with SteamOS. It's overall pretty good, but it is very unpolished right now for this deployment of it. It's a lot different from the deck, which has had a few years to develop. So that's kind of where it stands. I think the impression I got back in November was they were maybe trying to hit an $800 price point or something, and it's not possible. Valve would have to subsidize it so much that it would probably be submitted as an exhibit in the monopoly lawsuits against them. So something to think about as well. That's it though. Really in-depth. Hope you liked the review and all the use of all our tools and gear here. Subscribe for more as always. Go to store.gamersnexus.net to support us directly. If you want to buy one of our plates we've made, confirm your order first, I guess, with Valve. It sounds like they're going to be backlogging it a bit, but we'll have them on the store for you. It will directly support the work we do, like on the complicated videos like this one. And it also is something that we're making here. The current team is making it, which makes that really fun. We're doing the assembly, getting the magnets in there for you. So anyway, head over to the store if you want to grab one of those. And you can, of course, also grab one of our other items if you want to support us, but you're not buying a Steam machine. That's it. Thanks for watching. See you next time.